All right, so we'll get started. So next Tuesday we'll have our exam 2. Okay, so then on Monday we'll meet online. On Tuesday we'll be in seat. We are switching the two dates classes. Homework number 7. The next homework will be due the 1 week after the exam. Okay, number 2. But it's online already, so it's on that one. For the classroom disinfection, I assigned it to Owen and Jeffrey today. Okay. So today we'll be looking into new chapter here, chapter 8. This is not in the exam. So exam 2 will be covering chapter 3 through 7 in volume 2 of a university physics textbook. Okay. And also the content in the homework number 4, 5, and 6. Right. Okay. So this chapter deals with capacitors and capacitance. So for capacitors, it's the device that stores both energy and charge. So because it has that capacity, so it's called a capacitor. Okay, the name is kind of quite straightforward. So basically, the simplest one you can have is the two plates, metal plates, that is, you place them parallel to each other with a separation of D, okay, and then it's a capacitor. So you can charge the capacitor by using a battery like this, all right? A capacitor could also be, so this is a cross-sectional view of it. So you can imagine you have two sheets of metals and they are separated by an insulator, and then you can roll the two sheets together into a cylinder. So then this is a cross-sectional view of the cylinder. Okay, then it's a capacitor as well. Okay, and you can also charge the capacitor with a power supply or battery like that. So the capacitance of the capacitor is defined as the charge you build up divided by the voltage across the two plates. Okay, so it's Q over V. Q is in coulombs, V is in volts for the SI units. So that's the SI unit for capacitance, coulombs over V over volt. It has its own name called Farad or F. Okay. So these are some types of the capacitors you could have. So this this cylinder one is actually inside. It has that two metal sheet insulated by a insulator and then rolled into a sheet like that. Okay, you can roll the sheet into different shapes like this one. On this guy here, circular. This is two circular plates separated by an insulator in between. Okay, it's not, you cannot see it from the outside, but that's what it is. All right. And then there are different other different types of shapes over there. In a circuit, so if you have a capacitor, then it's represented by this guy. Okay, so normal capacitor is represented by this sign, which two lines next to each other, parallel to each other with a gap. The two lines are the same length, so that's a capacitor. If you have two lines, one line is longer, the other one is shorter, then that's a battery. Okay, so this is a capacitor. If this is a electrolytic capacitor, then it's slightly different. Okay, so with a curve on one of the lines. If you have a variable capacitor, the capacitance can be changing. Then you put the arrow on that. Okay, on that capacitor, that means it's varying capacitor. All right, so let's take a look on the simplest one you could actually make. It's just put two pieces of metals and then put them close to each other, then it's a capacitor. So when you charge the capacitors, you are building up charges on the two capacitors, okay? So this is done with a power supply or a battery. So then in that case, the charge will flow onto the two plates. On one plate, you'll build up positive Q, the other plate, you'll have negative Q, okay? That's due to charging neutrality from the battery over here. So if you have positive flow here, then negative Q will flow to the other one, okay? So the magnitude of the Qs will be the same. in the equation of C equal to Q divided by V, okay, then it's referring to the Qs on the two plate, okay, the absolute values of Qs. So if you have Q deposit on the plate here, then if this is uniformly distributed, then the surface charge on the plate is equal to sigma is equal to Q divided by the area of the plate, okay? Then in the previous chapter, we know that then the E field inside the two plate is sigma over epsilon naught, okay? So for one plate is sigma over 2 epsilon naught. You have two plates, one is positively charged, the other is negative charged. Then the electric field multiplies, okay? Actually doubles, so 2 times of that. So it's sigma over epsilon naught. Then the voltage across the two plates, you can calculate voltage is equal to the electric field times the distance. All right. So then electric field is sigma over epsilon naught times D. Then for sigma is Q over A. So then it becomes QD over epsilon naught times A. So then for the capacitance of this capacitor will be, according to definition, capacitance is equal to Q over V. V is this expression, you take that one in here. So then it's QD epsilon naught A. And then it becomes epsilon naught times A over D, okay? So then here you can see C is just equal to that. This is a constant epsilon naught. Now A is the area of the capacitor plates. D is the separation. So you can see capacitance is proportional to the area of the plates, and then inverse proportional to the separation D. Okay, so just determined by those two factors. Okay, it's not determined by the battery, the voltage of the battery, because capacitance is Q over V. Okay, in that sense. All right. Let's take a look on a quick example here. So this one says the plates of an empty parallel plate capacitor of a capacitance 5.0 PF. So P stands for pico, all right? Which is 10 to the negative 12, all right? And then it says 2.0 millimeters apart. What's the area of each plate? Okay, so we can, I think we can take a quick look on this one together. Using the equation we just derived in the previous slide for the capacitance of a parallel plate capacitor, this is C is equal to the epsilon naught times A over D. Okay, we are given the C, we are given the D, right? You are looking for the area. This is the constant 8.85. So you can rearrange the equation. Area should be equal to C times D over epsilon naught. So then this is 5.0 times 10 to the negative 12 picofarad given 2.0 times 10 to the minus 3 meters. Okay, you convert into meter from millimeter to meters, and then over the 8.85 times 10 to the minus 12 in farad over meters. Okay, so that gives you the area is 1.1 about times 10 to the negative 3 meters square. Okay, I think it's just 1.1, 266. All right. Any questions you guys might have on this guy? If not, we are going to take a look other types of capacitor you could have. Okay, so this is another type of capacitor you can have. You can have two metal pieces. This is again is a cross-sectional view of it. So this is made of two kind of spherical shells. Okay, inner one and outer one. And then you can charge the two shells, two pieces of metal here. So with positive charge here and negative charge there. Okay. So if you charge the two metals like that, then what will be the capacitance of this spherical capacitor? Okay. Now we will start with C equal to Q divided by V. All right. And then we are going to assume that the Q on the two metals, the metal spheres or shells, is going to be positive Q on one and then negative Q on the other one. Okay, so this is what we have then. Positive Q here, negative Q there. Then we have Q there, so we need to have V in order to calculate C, which is Q over V. All right, so then the first thing to do is to calculate V from here to here, from the inner shell here to the outer shell over here. Okay, so you need to do that by doing integration. Okay, from this is to calculate what's the electric field between the two shells first. Okay, so you get that electric field. So basically, this is applying Gauss's law. This is to calculate electric flux from the definition. Okay, so you draw a Gaussian surface in the dashed line over here. This is a spherical surface. So at distance r away from the center, your electric field should be having the same magnitude of E times the area 4 pi r squared. That should equal to the Q, the charge enclosed by this Gaussian surface. Okay, so that's the Q, positive Q over epsilon naught. From here, you can solve for E for the magnitude. So it's Q over epsilon naught, then divide by 4 pi r squared. So you rearrange the terms, put the constant terms together, 1 over 4 pi epsilon naught, Q over r squared. Okay, and that's in the radial direction of r. Okay, so the r hat is that guy. Now, given E, you can calculate what's your electric potential difference from the inner shell here to the outer shell. Okay, so then you integrate. This is the equation you use to figure out what's the potential. All right, or potential differences from 1 to 2. So E dot dl. Okay, so E is this guy dot dl. Dl is r in the radial direction. Okay, so then basically you can put the non-variables before the integration. So Q is fixed, 4 pi epsilon, they are also fixed. Okay, so you are basically integrating r squared, 1 over r squared, which will give you 1 over r, and then plug in the two limits, okay, r2 and r1 there. Okay, there's one step missing here. From integration, or from integration to the final step here. So if you are integrating 1 over r squared, it gives you minus 1 over r, right? When you do integration of it. So minus 1 over r, let me write it down here. Q over 4 pi epsilon naught integration r1 to r2, 1 over r squared dr. Okay, so this integration will give you minus 1 over r. Okay, and then r1 to r2. Okay, so that equals to Q over 4 pi epsilon naught. In that case, you'll be doing minus 1 over r2 minus 1 over r1. Okay, so that's how you get the 1 over r1 minus 1 over r2 in the parentheses. Okay, so that's Q over 4 pi epsilon naught will be your V. Okay, and you can further rewrite this 1 over r1 minus 1 over r2 to be doing common denominator here, r1 times r2, and then r2 minus r1 on top. Okay, so you can rewrite it as that. So your V will be equal to Q over 4 pi epsilon naught R2 minus R1 over R1, R2. Then when you do Q over V, all right, so the next you are calculating your capacitance, C equal to Q over V, then that will become C will be equal to Q over V, so Q divided by this thing, Q over 4 pi epsilon 0, R2 minus R1 over R1 times R2 at the bottom there. Okay. So Q and Q will cancel out. 4 pi epsilon naught becomes numerator, and then R1, R2 becomes also numerator. R2 minus R1, okay? So then that will be your capacitance for such types of capacitor. So the procedure, again, as listed on the slide, you have to go follow the steps over there. Okay, so first figure out what's V. You need to figure out E first and then figure out V. So then do C equal to Q over V. That will give you the capacitance of a capacitor. Okay. Any questions you guys might have on this derivation? If not, we'll take a look on a different type of capacitor. In this time, we are looking at a cylindrical capacitor. So basically, this is made of a piece of metal in the middle, and then the outer shell is a second piece of metal. Okay, so you can think about the cables we have at home. As in the middle, it's a metal piece, and then there's the outer shell, a sheet of metals together. Okay, so that could be also a capacitor. Now, what will be the capacitance of a capacitor like this? Okay, so again, you will be figuring out what's the electric field between these two metal pieces. Okay, you draw a Gaussian surface like that, as a cylindrical part. Okay, and the electric field will be from positive to negative, so it'll be pointing outward. Okay, radially in radial direction. And you integrate your Gaussian surface on the two sides, about two buttons. Flux will be 0, so then only the side surface will give you the flux. So E times 2 pi r times the length. Okay, so that gives you the side area. According to Gauss' law, it's equal to the Q enclosed divided by epsilon naught. Okay, so Q enclosed is the Q here, enclosed by this cylindrical here. So from here, then you get your electric field is 1 over 2 pi epsilon 0. Okay, so basically divided by the right hand side by this 2 pi r times L. That gives you the E field. Okay, Q over R times L in the radial direction. Then V, the electric potential difference between the two metal pieces, you can calculate in this fashion. Okay, so again, E dot dl. You can again move the non-variables before the integration. In this time, you are integrating 1 over r, all right, of dr, which will give you natural logarithm function of r. Okay, so integration will become natural logarithm of r. All right, then you plug in the two limits there, q over 2 pi epsilon naught times L ln of R2 over R1. Okay, so this is your V. Then C is equal to Q over V. Again, Q and Q will cancel out. Then this is your final result. Okay, so this is how you will be doing calculating the capacitors for cylindrical capacitor like that. Okay. All right. Let me know if you guys have any questions on this. Okay. If not, then we'll move on to the next section. So a lot of cases, you have more than one capacitors in a circuit. So for example, in this scenario, you have 3 capacitors connected one after another. Okay, that's the three capacitors in pink, and then charged by a battery. Okay, so then what would be this overall capacitance of these three if you connect them one after another? Okay, so if you have them connected one after another, we call them in series. Okay, in that case, they share the same charges. You can see, so if positive Q is deposited under here, then according to charge neutrality, you should have negative Q deposited over here. And then on the other side, you should have positive Q, due to this is a capacitor. In one side, you have negative Q, the other side should have a positive Q. So you can see then this wire initially should be charge neutral. Then if you bring positive Q on this side, then negative Q will be on that side. Similarly over here, if you have positive Q here, you have negative Q there, then positive Q will be here, okay? So you can see across each of these capacitors, they share the same charge, okay? If they share the same charge, they are in series, all right? In that case, the overall capacitance of those in series, you can represent it with an equivalent capacitor, okay? So that has the equivalent capacitance of those three combined. It will be given by this equation. So the equivalent, 1 over the equivalent is equal to 1 over C1 plus 1 over C2 plus over C3, okay? And we can kind of see how that's the case, okay? We can derive this guy here. So let's take a look on this case that you have them connected one after another. There are three of them. Okay, so let's draw this as a longer line, shorter line. That means this is a battery. And these three are capacitors. They are about the same lines, each other. So positive Q here, negative Q there, positive Q here, negative Q there, and then positive Q here, negative Q there. And then this is epsilon, the voltage across the battery, okay? So if they are connected in this case, so then we can see this is C1, this is C2, this is C3, okay? Capacitor 1, capacitor 2, capacitor 3. And then we can represent the capacitance by using C1, C2, and C3, okay? So in that case, we can see the voltage or the potential difference across the capacitor, the V1, okay, should be, so V1 should be equal to, according to the equation that C equal to Q over V, so then V1 should be equal to Q over C1, okay? They share the same Q, so I don't need to specify Q1 because Q1, Q2, Q3 are the same, and they are written as Q. Potential difference across the second capacitor should be equal to Q over C2. Potential difference across the third capacitor should be equal to Q over C3, okay? And you can see the potential difference across each of these three capacitors add up should be equal to the potential provided by the battery, right? So basically, it tells you V1 plus V2 plus V3 should be equal to that epsilon, okay? So you can write Q, not Q1, Q over C1 plus Q over C2 plus Q over C3 equals to epsilon, okay? And we say you can use an equivalent capacitor to represent the three in series. So this is your CEQ to represent those three. And this is epsilon. So then in that case, this is equal to, so if, yeah, so you will have positive Q, right? Created by this battery over here, and then negative Q over there. So then it will be equal to Q over C of equivalent, okay? So if you represent just by one capacitor, okay? So in that sense, the Q's are the same across the terms, so those can cancel out, okay? So then you end up with 1 over C1 plus 1 over C2 plus 1 over C3 equal to 1 over CEQ, okay? Which is the equation shown on the PowerPoint slide, okay? If you have 3 of them in series, then that's the result. So to calculate this CEQ, you actually, so note this is inverse of CEQ. So then CEQ should be equal to 1 over C1 plus 1 over C2 plus 1 over C3, and then take inverse, okay? If you would have to calculate CEQ, you do it that way, okay? After you do inverse of each capacitance of capacitors, and then do inverse again, all right? So if you have more than 3, you add the rest up, 1 over inverse of the capacitance up, okay? If you just have 2, then it's 1 over C1 plus 1 over C2, all right? Any questions you guys might have on that? All right. So if not, then another configuration of combination of capacitors, you might have capacitors in this case now in parallel to each other, okay? So if they are connected this way, all right, and then they can be powered by a battery or a power supply at those 2 terminals, okay? You can say positive terminal or negative terminal, positive and negative that way. So you can see if they are connected in that way and then powered by a power supply or battery, then they will share the same voltage across the capacitors, right? So voltage across these 2 should be equal to VA minus VB. And then on this one should be also VA minus VB. And then on this one should be also VA minus VB. Okay. In that case, they are in parallel. Okay. So if they share voltage, then they are in parallel to each other. When they are in parallel, then you can represent the combination with one single equivalent capacitor, with a capacitance of CEQ. The result will be equal to C1 plus C2 plus C3, okay? And then if you have more than 3, you add the rest up, okay? So when capacitors are in parallel, you just add up their capacitance up for the equivalent resistance, okay? And we can also derive this equation, so we can you can see that. So if they are parallel to each other, so then this is what we would have. If between this is V, the difference is V, this is C1, C2, C3, okay? Then in this case, we can calculate the total charge, Q total, on the capacitors, okay? That should be equal to Q1 plus Q2 plus Q3. Now again, C equal to Q over V, so then Q1 is equal to C1 times V, okay? You have the same V, so V1, V2, V3 are the same. Q2 will be C2V, Q3 will be C3V, all right? And if you represent the combination with a single capacitor, CEQ, all right, so that's V between those 2 terminals, then total will be equal to CEQ times V, okay? In this case, your V's are the same on those terms, so then that cancels out across. So your CEQ will be simply then C1 plus C2 plus C3, okay? If you have more than 3, you add the rest up. You have less than 3, and then just C1 plus C2. Okay, so that's when they are in parallel to each other. Okay. Now later on, we are going to also learn the resistors in serial and in parallel. So in that case, it's the other way around. Okay, so when we get to that, we'll see about that. All right. Now in reality, you might well have the scenario of the combination of resistors in series and in capacitor. Okay, so in this case, let's say you have the 2 terminals A and B can be connected to a power supply or battery, and then you have the 3 capacitors. In this case, they are connected in that fashion. So you can see these 2 are in series. All right. Now the combination of these 2 is in parallel with that one. Okay. So when you have combination of capacitors in series and parallel, so you want to look into the part that you have just purely capacitor in series or in parallel first, okay? And then represent that part by an equivalent resistor. And then starting from there, you will move on and then look on the part that is purely, again, in series or in parallel. Let me see if there's another one, okay? All right, so on this one, I can get you guys started, and then you can try to see if you can solve for the equivalent resistance here, our equivalent capacitance. $15 microfarad here, 8.2 microfarad here, and 22 microfarad. All right. So if you take a look on this one, you can figure that these 2 are in series with each other. Okay, so that's the part of the circuit that is only have capacitors purely in series with each other. Okay, so then you can replace that one with equivalent. So I'm going to call this as C1, this as C2, and then this as C3. Okay, so I can replace that with equivalent capacitor called C12, combine of 1 and 2. So because they are in series, all right, so then this guy will be equal to 1 over C1 plus 1 over C2. Inverse. Okay, you can take calculate what's that one first, and then you will take the inverse of it. It gives me 5.97 microfarad. So then my circuit will be becoming just a C3 in parallel with the C12. C12 is the equivalent of 1 and 2. Okay. I guess we can do it this together. So if they are in series, then in this case they are in parallel. Sorry. So in parallel, so then the total equivalent should be just C12 plus C3. Okay, because they are in parallel. So 5.97 plus 15. Okay, that will be about 21 microfarad. Okay, that's your final result there. Now you might be given a much more complicated one. Okay, so let me and then I think you are going to see one similar to this in your homework assignment. Okay. So let's say you have a circuit like this. So these are all capacitors. Okay, so you can call C1, C2, C3, C4, C5, and C6. Then you are asked to find what's the equivalent between A and B for the whole stuff here. Okay. So in that case, you can see in this part of it, they are purely in series. That's one after another. Okay. And then if you replace this with a C12 equivalent of 1 and 2, then this now becomes C12, and then a C3 here. All right. On this branch over here, you can see this guy is in series with these two together. These two are in parallel to each other. So you want to treat these two as equivalent one first, C5 and 6 first. Okay. So then this would be a C4 followed by an equivalent of C5 and 6. All right. So then if you look at, again, in this case, these two, you can treat them as just one equivalent capacitor of C456. Okay. So this simplify as that, and then this will further simplify as now you would have C12, a C3 here, and then a C456 together. All right. Now these three are parallel to each other. Okay. So then you can add this guy plus that guy plus that guy up. Okay. All right. Questions you guys might have? Okay. If not, we are going to take a look on the next topic about capacitors. This one deals with disconnected and reconnected capacitors. Okay. So for capacitors, you want to charge them. Okay. So you probably will first connect them to a power supply, right? And then charge them. And then after that, you disconnect it from a power supply and then connect to the another device. Okay, so that's basically like you guys are doing this every day. Like for your cell phone or your battery, you charge it, right, and then disconnect it, and then the power stored in the capacitors are used for the phone or the laptop. Okay, but let's take a look on this one here. So it says if you have two capacitors, a 100 picofarad and a 400 picofarad capacitor, they are both charged to 2 kilovolts. They are then disconnected from the voltage source and are connected together, positive plate to negative plate and negative plate to positive plate. It's asking you to find the resulting potential difference across each capacitor. All right, you can think about how you want to do this as I draw the figures on my paper here. So it always helps if you sketch the problem. So let's see here. You have two capacitors. They are both charged to 2 kilovolts. So that means they have the same voltage, right? So they are parallel to each other. Okay. So A and B, that's the power source. And the terminals are power source connected to. Let's say this is 100 picofarad. This is 400 picofarad. Okay. When you charge them, okay, put the power source up. So VAB across this A and B is 2 kilovolts. All right. When it's charged to 2 kilovolts, you'll expect that, let me say this is positive terminal, this is negative terminal. You would expect then positive charge on this guy, right? So positive Q on this one. If we call this capacitor 1, then let's say charge Q1 here. Then on the other plate, you should have negative charge Q1, okay? On this capacitor, then this will be charge Q2 on the top plate minus Q2 on the bottom plate, okay? So you will have charges built up, okay? Now you can calculate Q1 and Q2, okay? So for this, Q1 will be equal to C1 times V, okay? According to C equal to Q over V, so Q will be C times V, okay? So 100 pico times 10 to the minus 12 times 2 kilo times 10 to the third volts, okay? That will give you 200 times 10 to the minus 9, that's in coulomb, okay? Or you can say this is 0.2 microcoulombs times 10 to the negative 6, okay? So if you convert into microcoulombs, either way, it doesn't matter. You can also calculate what's Q2. So Q2 will be C2V 400 minus times 10 to the minus 12, 2.0 kilo. That will give you 800 times 10 to the minus 9, or 0.8 microcoulomb, okay? So this is what you initially have. You charge the two capacitors to 2 kilovolts, okay? You build up two charges on the two capacitors, Q1 and Q2. Now, what happens next? You disconnect them from the power source, okay? So you disconnect them from the power source. That means you cut off the power source. But you reconnect them in the fashion that so positive Q1 minus Q1. You reconnect that. It says the positive plate to the negative plate. So you flip the two, okay? Flip the capacitor 2. So then this is minus Q2. Yeah. So basically you keep, let's keep capacitor 1, and then we flip capacitor 2, right? So then Q1 positive plate to negative plate, and then negative plate to positive plate. Okay, so this is after you reconnect them. This is what happens after you reconnect them. Let's see. So the problem asks you to find the resulting potential across each capacitor. So that means V1, let's say prime, okay, and then V2 prime. So if you have them reconnect this way, you can expect what's happening here is because now there's positive charge, right? Connect to negative charge. You can see there will be redistribution of charges, right? The positive will flow to the negative side, and at the same time, the negative will flow to the positive side. Okay, and then also on this, the bottom plates, they will have charge redistribution again. Okay. So the result would be, we can see that Q1 is 0.2, Q2 is 0.8 in microcoulombs, right? So Q2 is larger than Q1. So you can expect that after that, positive Q1 on top will be neutralized by part of Q2. So then you will have negative charges on the top plates, okay? So what happens afterward is, after redistribution of the charges, you would have then probably negative of Q1 prime this time, all right? And then negative of Q2 prime here. On here, you will have positive Q1 prime, positive Q2 prime, right? That's what's going to happen afterward, because Q1 is less than Q2, okay? Now, in this case, we can see afterward, because the top plates are connect together, the bottom plates are connect together, right? So if you have voltage across this guy, the place of capacitor 1, then that will be the same voltage across the second capacitor, right? Because the top plates are connected and then the bottom plates are connected, okay, by a wire. So you would expect that V1 prime would be equal to V2 prime, okay? Let's just call that as V prime. So you can figure that they are in parallel, okay? After they are reconnected again, okay? They are still in parallel, okay? So then the question is, you just need to figure out V prime, okay? The total voltage across, okay? So they are in parallel to each other. You can calculate what's the CEQ of the two, right? When they are in parallel, you do just add them up, right? When they are in parallel, you add the two up. So then it becomes 500 picofarad, 100 plus 400, okay? You're looking for this guy. So then what you need to know is what would be the Q total, right? Prime afterward, okay? So Q total prime, you can see will be on the top plate will be the two add up, right? Redistribution add up, and then the bottom also you add them up. Okay, so Q total will be equal to them. In this case, because Q2 is greater than Q1, then it will be just Q2 minus Q1. Okay. On the bottom plate to be positive, and then on the top plate to be negative of that. Okay. So let Q prime total is Q2 minus Q1, which is 800 nanocoulomb minus 200, or 0.8 micro minus 0.2. So let me see, what did I use? So either way, it doesn't matter. So 0.8 micro minus 0.2 micro, which gives you 0.6 microcoulomb. Okay. So you have your Q total, you have this guy, then you can calculate for the voltage. Okay, so voltage should be equal to the Q total prime over C equivalent. Okay. Our voltage should be prime. We are looking for V prime. So 0.6 times 10 to the minus 6 coulombs over CEQ of 500 pico minus 10 to the minus 12 times 10 to the minus 12. Okay. That will give you 1.2 times 10 to the third volts. Okay. and that should be both the for both the potential on the two plate two capacitors. Okay, they would have the same because they are in parallel to each other. Questions you guys might have? All right. So if not, we will take a look on the next section. So energy stored in a capacitor. So basically, a capacitor stores charge and energy, right? So then, I think we have take a look on how to calculate the charge, but let's take a look on how much energy will be stored in a capacitor. Okay, so when you are charging a capacitor, you basically move the charge from the negative plate to the positive plate by using a power source or a battery. Okay, so then you are moving that slowly, dq. Okay, so over there. So at the same time, if you have q built up, then you have voltage built up, okay, across the two plate. Okay, so then the energy store in the process of moving a dq charge from one plate to another place is equal to the dq times v. Okay, v you can calculate, it should be q divided by c. And to calculate the energy stored, you will do integration of du. Okay, so and the process is starting from when you have zero charge on the plate up to you have your final charge q on the plate. Okay, and then dq. In that case, you are seeing q is your variable, so q over c dq will give you 1/2 q squared. Okay, and then there's c in the denominator, so 2c q squared. Okay, that will be the energy stored in the capacitor, so q squared over 2c. Now, because you can write c in this case in terms of q over v, all right? So then it can also be rewritten as 1/2 q times v, or if you rewrite q as c times v, then it's 1/2 cv squared. So any one of those three expressions should be valid. Okay. So this is basically you are using the relationship of C equals to definition of capacitance C equal to Q over V. Okay, so we have U equals to Q squared over 2C. If you rewrite C as Q squared over 2 times CS, so C is Q over V, right? So then this is square. Okay, so then you can see Q will cancel out the square, the V will flip up, so it becomes Q half of Q times V, right? So that's the second expression. Or if you don't do it that way, you just rewrite the Q as C times V, then this is CV squared over 2C, okay? So it's C squared V squared over 2C, then C and C cancel out there. You still have one C on the top. So then 1/2 CV squared, okay? So basically, that's how the other two expression came from, right? So any of those three could give you the potential stored in the capacitor. All right. So energy stored in the capacitor is equal to 1/2 QV. We'll just pick one of the expression there. Then we can calculate what would be the let's see. Okay, so in this case, you just rewrite V as E times D, the electric field times the separation of the two plates. Okay, and then Q is epsilon 0 times E times A. That's coming from again C times V. So this is where it comes from. Okay, so energy U is equal to 1/2 Q times V, and then Q is equal to C times V. Actually, no, it's not from there. So Q is basically from so for two plate, the parallel plate capacitor, we know E field is equal to epsilon times 0, right? So then in that case, sigma, you can calculate sigma will be equal to epsilon naught times E, right? Sigma is charge over area, okay? So then these two equal to each other. So then Q equals to epsilon naught times E times area, okay? Not that, but Q equals to that guy. So this is 1/2 epsilon naught times E times A, and then V is E times D, okay? So you can see then this is 1/2 epsilon naught E squared times A times D. A is the area, D is the separation of the two plates. So A times D is the volume, okay? Volume of the plates, the capacitor, the two. So this is volume. If you do energy divided by volume, okay, then that gives you energy density, okay? So which is this slide about, okay? So then electric energy stored in the capacitor divided by volume will be just equal to this guy, okay? 1/2 epsilon naught times E squared, okay? All right, and then we should note at least up to this point, we haven't talked about the insulator in between the capacitor. So this is just a free space separation. That's just vacuum in between the two plates, okay? All right, I think we'll stop here. Again, on Monday, we'll see you guys online, okay?